In this video, we will be talking about the ideal gas law, as well as some of the standard conditions under which measurements are typically made, such as the standard ambient temperature and pressure and standard temperature and pressure. We will also look at a couple different calculations using the ideal gas law equation. In a previous video, we talked about some of the laws for gases: Charles' law, Boyle's law, Avogadro's law, and Gay-Lussac's law. In each one of those laws, essentially two variables, pressure, volume, number of moles, or temperature, were being varied and looking to see how the two were related to each other. In Boyle's law, what we found was by looking at the relationship between volume and pressure are inversely related to each other. Essentially, your pressure is equal to some constant times 1 over your volume, or you could express it as your volume is equal to some constant times 1 over your pressure. In this case, we will find that the constant is N, the number of moles, times R, this constant, which we will call the ideal gas law constant, and T, which is temperature. Looking at Charles' law, there was looking at the relationship between volume and temperature. We found that volume is directly proportional to temperature. As temperature goes up, volume goes up. So it was volume is equal to some constant times temperature, and we will find that that constant is the number of moles times the gas constant, R, divided by P. Another one, Avogadro's law, which was looking at the relationship between volume and number of moles, found that the relationship was directly proportional. As volume goes up, number of moles go up, or as number of moles go up, the volume goes up. And the volume was equal to some constant times the number of moles. That constant we will see is the ideal gas constant times T over P. So when we combine all of the four various laws together, we find that our overall equation is PV equals nRT. So if we take pressure times volume, that's equal to the number of moles times our ideal gas constant times temperature in Kelvin. When you go and look at tabulated values, what you'll find is that a lot of them are done under very specific temperature and pressure conditions. There are 4 standard conditions that get used for tabulating data. The first, and one that is primarily used by chemists and physicists, is standard temperature and pressure. The definition is of this is 1 bar of pressure and a temperature of 0 degrees Celsius or 273.15 Kelvin. The 1 bar is the same as 10 to the 5th pascals. Again, this is the one that is used in chemistry and physics. In biology, the standard condition is standard ambient temperature and pressure. The pressure is the same as standard temperature and pressure, but the temperature is raised to 25 degrees Celsius. The reason for this is that at 0 degrees Celsius, most of your biological species that would be held in like an aqueous medium tend to die. And so it's much more convenient to be working at sort of room temperature, which is where a lot of your bacteria are going to be thriving and surviving. So standard ambient temperature and pressure is the one that gets used a lot more often in biology. There's also normal temperature and pressure, which is 1 atmosphere of pressure, which is 101.325 Pascal, and 20 degrees Celsius. This one is primarily used by the EPA and NIST, the National Institute of Standards and Technology. In the Trove book, it's using an outdated version of standard temperature and pressure, where the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. This particular version of standard temperature and pressure was replaced in 1982 by our current standard temperature and pressure, which is a temperature of 0 degrees Celsius and a pressure of 1 bar. Let's now look at an example of how we can use the ideal gas law equation to solve some problems. So the first one we're going to look at is to determine the molar volume of an ideal gas at standard temperature and pressure. Molar volume is simply the volume that 1 mole occupies. So that would be, we're essentially looking for V over N, the volume per mole of gas. So we can start with our ideal gas equation, PV equals nRT. We want to get the N on the left-hand side and the P on the right-hand side. So what we'll do is we'll divide both sides by N, and then we'll divide both sides by P. Now on the right-hand side, our N's cancel out. On the left-hand side, our P's cancel out. So we now have an equation, V over N is equal to RT over P. We can now plug in our values. For R, this semester we're going to be using 8.314 Pascal meter cubed per mole Kelvin. The reason that we're going to be using this value is that when you take pascals times meter cubed, this is the same as a joule. We're going to be using R for both gases as well as when we're in the kinetics and thermodynamics. We'll be using this 8.314 in those chapters as well. So we're going to be continually using this value, which is why we're not using some of the other various forms of R. So plugging in our values, for R, it's 8.314 Pascal meter cubed over mole Kelvin. Okay, so we're going to get rid of our Kelvin on the bottom, so we're going to multiply by the temperature at standard temperature and pressure, which is 273.15 Kelvin. Our Kelvin are going to cancel out, leaving us with Pascal meter cubed over mole. We will then multiply by the reciprocal, or the same thing as dividing, by the pressure. So that's 1 over the pressure at standard temperature and pressure, which is 10 to the 5th pascals. Our Pascal are going to cancel out. This leaves us with meters cubed per mole. But liters is a much more commonly used volume than meters cubed, so let's convert it to liters. So to do that, we need to find the relationship between meters and liters. A liter is by definition a cubic decimeter. So if we can convert the meters to cubic decimeters, then we can do a 1-for-1 conversion to liters. So we're going to do that by putting meters on bottom. 1 meter is 10 decimeters. We cube this because we have cubic meters. Cube. And then our units, the meters cancel out, leaving us with cubic decimeters. And then we can convert that to 1 liter is 1 decimeter cubed. Our decimeters cubed cancel out, leaving us with liters over mole. If you plug this into your calculator, this would be V over N, the volume that 1 mole of gas occupies. You will sometimes see this as V sub M for the molar volume. This is equal to 22.70696 liters per mole. In terms of significant figures, our R value has 4, our temperature has 5. The Pascal, this is an exact definition for standard temperature and pressure, so this does not come into play, nor do our conversions between meters and decimeters and liters and decimeters. So we will have 4 significant figures, and so our value would be 22.71 liters per mole. Okay, now if we want to determine the molar density of nitrogen, N2, at standard temperature and pressure, the molar density is pretty much the inverse of molar volume. The molar density is the amount of moles that will fit into 1 liter. So that is N over V. So we're going to do the same thing we did before, start with PV equals nRT, but this time we want N over V. So we will divide both sides by V to move it to the right. And then we want to get rid of the RT on the right-hand side, so we'll divide both sides by RT. And look to see what cancels out. The V's on the left-hand side cancel out, and the RT on the right cancels out, giving us an equation: N over V is equal to P over RT. We can now plug in our values. The P is the pressure at standard temperature and pressure, which is 10 to the 5th pascals. We're going to multiply this by the inverse of our gas constant, 8.314 Pascal meter cubed per mole Kelvin, 1 on top. Our pascals are going to cancel each other out. We can now divide by our divide by our temperature to get rid of the Kelvin. So that is the temperature at standard temperature pressure, which is 0 degrees Celsius, so 273.15 Kelvin. Our Kelvin cancel out. So this will give us moles per cubic meter. Now again, liters is more commonly used. So we can do a similar conversion, but this time it'll be inverted. So we want to get rid of the meters, convert it to liters. So we'll need meters on top, decimeters on bottom. 1 meter is 10 decimeters. It's meters cubed, so we have to cube this conversion. And then 1 decimeter is 1 liter. In terms of canceling out units, cubic meters cancels out our meters here, decimeters cancels out decimeters. This one should be cubed. Our decimeters will cancel out, leaving us with moles per liter. If you plug this into your calculator, what you'll find is the N over V, which you could also write as 1 over V sub M, is equal to 0.044039361 moles per liter. In terms of significant figures, R has 4, our temperature has 5, and so we will end up with 4 significant figures. So our end answer would be 4.404 times 10 to the negative 2 moles per liter. Last one, we're going to try to figure out how much does 2.51 liters of H2 weigh at standard temperature and pressure. So to figure out how we're going to do this, anytime we're trying to find weight or mass of something, we typically use the molecular weight. To do that, we go from moles times the molecular weight gets us to the weight. So we have liters, which is a volume. We can use our ideal gas equation to go from volume to moles, and then we can go from moles to weight. So what we want to do is take our ideal gas equation and solve for number of moles. So we can take our PV equals nRT. We want N by itself, so we're going to divide both sides by RT. If we do that, RT cancels out, giving us N is equal to PV over RT. So to plug that in, we'll need to write out our numbers. So our pressure is 10 to the 5th pascals. We're going to multiply that by our volume, 2.51 liters. We're going to divide that by our R value, or multiply by the inverse. So that's 1 over 8.314 Pascal meter cubed mole Kelvin. Look to see where we are. Pascals will cancel out. Liters and meters don't quite cancel out. We will need to do a conversion. So let's do that so we can cancel out some units. Meters cubed, 1 meter is 10 decimeters. We will cube that. Our meters cancel out, leaving us in cubic decimeters. We can then take this, multiply that by 1 decimeter cubed is 1 liter. Our cubic decimeters cancel out. Our liters cancel out. We still have Kelvin that we need to contend with, so we're going to multiply this by the temperature at standard temperature and pressure, which is 0 Celsius. So we will take that, divide by 273.15 Kelvin. Our Kelvin cancel out, giving us moles. The last step, we want to find the weight. So we can take our weight. The way we're going to find our weight is convert to grams, get rid of moles, and we just plug in our molecular weight, which is 2.01588 grams. Our moles cancel out, giving us grams. Okay, so if you plug this all in, the mass, our answer, would be equal to 0.222861 grams. In terms of significant figures, we have our volume here with 3, R has 4, temperature has 5, molecular weight has 6, and so the least of those was 3, so we'll cut it here. So our end answer would be 0.223 grams. Okay, now this one is a problem for you to try. So what I want you to do is pause the video and try to solve this. When you're all done, hit play and we'll go through the work together. So pause now. Okay, so this one is very similar to the one we just did. The difference is we're now working at standard ambient temperature and pressure. So SATP. The only real difference that happened is our temperature went from 0 degrees Celsius to 25 degrees Celsius. So we're again going to be working with our molar volume. So that is V over N. So we'll do PV equals nRT. We want N on the other side. Divide both sides by N. We don't want P on the left, so we'll divide both sides by P. In terms of what cancels, our P's cancel, our N's cancel. We can now plug in our values. So this is 8.314 Pascal meter cubed over mole Kelvin times our temperature in Kelvin. We're now at standard ambient temperature and pressure, so that's 25 degrees Celsius. So that's 298.15 Kelvin. Our Kelvin cancel out. So we will now need to get rid of our Pascal. 1 over our pressure, which is standard ambient temperature and pressure, is 10 to the 5th Pascal. Our Pascal cancels out, leaving us with cubic meters over mole. We're going to again convert into liters. So that would be meters on bottom, decimeters on top. 10 decimeters is in 1 meter. Cube that because we have currently cubic meters. So our meter cubed cancels out. We're now in cubic decimeters. 1 liter is 1 cubic decimeter. Our decimeters cancel out, leaving us with liters per mole. If you plug this into your calculator, your V over N, which again, sometimes you'll see M with a V with a subscript M, is equal to 24.7882 liters per mole. In terms of significant figures, our R has 4, temperature has 5, so our end answer is going to have 4. So our end answer should be 24.79 liters per mole. Our molar density is sort of the inverse, so that would be N over V. It's the volume, or the number of moles that are in 1 liter of gas. So we'll take our PV equals nRT. We want N over V, so we want V to be on the right-hand side. So we'll divide both sides by V. And we want the RT to be on the other side. So divide both sides by RT. Right? On the right-hand side, RT cancels out. On the left-hand side, V cancels out. So we get N over V is equal to P over RT. Plugging in our values, pressure is 10 to the 5th Pascal. That's the definition of standard ambient temperature and pressure. We'll multiply this by the inverse of our R value, 8.314 Pascal meter cubed per mole Kelvin. Our pascals cancel out. We will now divide by temperature. So 1 over standard ambient means that we're working at 298.15 Kelvin. Our Kelvin cancel out. Okay, and now we have moles per meter cubed. Let's convert into liters. So that would be 1 meter is 10 decimeters. We have meters cubed, so we need to cube this conversion. Our meters cancel out. Then converting into liters, 1 decimeter is 1 liter. Decimeter cubed is a liter. So our cubic decimeters cancel out. So we're now in moles per liter. So N over V, if you plug this into your calculator, you will get 0.0403417 moles per liter. In terms of significant figures, 8.314 has 4, our temperature has 5, and so our end answer will have 4. Okay, so our end answer would be 4.034 times 10 to the negative 2 moles per liter. Okay, our last one. How much does 5.01 liters of O2 weigh at standard temperature, standard ambient temperature and pressure? So we want, again, we want weight. So we're going to try to convert things into moles. So we want essentially N. So if we look at our ideal gas equation, PV equals nRT, we want N all by itself. So if we divide both sides by RT, right, on the right hand side, RT cancels out, so we get N is equal to PV over RT. We now plug this all in. Our pressure is going to be 10 to the 5th Pascal. We can multiply this by our volume, 5.01 liters. Our R value, we're going to put that on bottom, so 8.314 Pascal meter cubed, mole Kelvin on top. Looking where we are, our pascals cancel out, our liters don't, so we would need to convert. A meter, 1 meter is 10 decimeters, cube that, and then 1 liter is 1 decimeter cubed. Meters cancel out, decimeters cancel out, so we now have, and our liters cancel out, so we now have moles and Kelvin. We want moles, so we need to get rid of the Kelvin. Kelvin's on top, so we're going to put our temperature on bottom. We're at standard ambient, so that's 298.15 Kelvin. Our Kelvin will cancel out, giving us moles. The last step is going to be multiplying this by our molecular weight. The molecular weight for oxygen, O2, is 31.998 8 grams per mole. Our moles are going to cancel out. Okay, so our answer would be 6.467353 grams. In terms of significant figures, our volume has 3, R has 4, temperature has 5, molecular weight has a lot more, has 6. So we're going to be cutting it at 3 significant figures. So our end answer will be 6.47 grams.